All right, now we start into electricity, and the first thing we start is we call it statics, and that's because what we're looking at is at this stage charges that are not moving. And in level 1, yeah, of course we looked at statics and we looked at DC and we looked at electromagnetism. So level 2 is quite similar to that. Let's just start by looking at a charge. Call that a positive charge. So that charge there is a proton. They're the only things that have positive charges, right? I didn't say how much the charge was. It could be millions of protons together. It could be just the fact that this piece of dust has lost some electrons, in which case it's positively charged. But the positively charged inherently comes from a proton. So anyway, what I'm doing here is I'm going to draw what's called field lines. What type of field lines? I hear you all ask. Electric field lines. So these are electric field lines. Now you came across in level 1 electricity magnetic field lines, which were quite similar. Remember, you'd have a magnet north, south, and we had these field lines that went like this, and they went from north to south. Well, this is similar, but field lines in electricity go from positive to negative. So this is field lines emanating from a charge. So the field line goes from plus to minus. So actually, if I had a negative charge over here, then that field line could go straight to it. And they do originate on the charge. So really, to be quite correct, I should have this. Now, there were no magnetic monopoles. So it wasn't like the magnetic field lines originated on a magnetic monopole. See, and I think you realize this, is that magnetic field lines are generated actually by charges, but charges that move. And that's why when we look at this, we're looking at statics. Charges that stay right where they are static, and they produce an electric field. When they start to move, they immediately also produce a magnetic field, which really is just a whole byproduct of this electric field, but due to this relative motion. So magnetism is really a relativistic effect, but we don't need to think about that. We just need to know that positive charges, there's a field that goes from plus to minus, and obviously field charges coming in. So these are fields, and the arrow is always going plus to minus. What we can have a capacitor. A capacitor is where we've got these two plates and we hook it up to a battery, and we end up with a positive charge on one plate and a negative charge on the other. And again, we got charges. They're just sitting there. They're not moving, not once it's charged. And so we get this electric field that goes from positive to negative. Now, the electric field strength, okay, so this really is the measure of the electric field at any point in space. Let me get another piece of paper like this. If we had a plus charge over here, we're going to have an electric field. Now, when I make an electric field, I use E, but I often will put that underneath it. You won't necessarily see that in all your classes or wherever. But the thing to remember is it's not E for energy, it's E for electric field. Same letter, so it causes some confusion, but it is E for electric field, and we're going to need to remember that. So going back to our diagram here, again, that's the electric field. What I'm saying, we get this positive charge, we get that electric field. If that had been a negative charge over here, and I said that, then at that point we would have had an electric field going towards the negative. Now, the electric field, what is it? We haven't really talked about what it is. And what it is it's a place where, so electric field is a point in space where an electric force is felt, and it's the force on a positive charge. So electric field, it's the force on a positive charge. So when we have this positive charge here, we're saying we now have what we're calling a field out here. And if I had a positive charge out here, we all know that same charges repel. That's because a force is felt that way, all right? So if that's the force on this charge, there must be an electric field there, and it's the electric field which produces the force on that charge. So really the electric field is just putting a bit more information into what we've always learned about for a while now, which is that opposite charges attract and same charges repel. Now if we had the negative charge here, then we're saying the electric field is that way, and that's because if we put again a positive charge there, remember this was a positive charge, it would feel a force that way. So the electric field just says there's a field out there, it's going to create a force, and the force is going to be in the direction that would, the field is going to indicate the direction a force would be felt on a positive charge. So that's the electric field. Now the electric field gets weaker and weaker the further away you get from a charge. All right. Now that means the electric field is changing, but in the capacitor, this one here, the electric field is what we call uniform. It's constant. It's the same strength. It's not getting weaker and weaker and weaker. And you can see there's a symmetry here that would create that. When you draw this, make sure that you do a little bit of a curvy bit at the end, just to show that there is still some field bulging out the ends of this capacitor. That's often the difference between merit and achieved. Alright, so that's a good start, electric field.